Did you know thermogravimetric analysis, often abbreviated as TGA, can measure the amount and rate of change in the weight of a material as it is heated, cooled, or held at constant temperature? This technique is a branch of thermal analysis, and the changes it measures can include, among others, chemical reactions, phase changes, and the absorption or desorption of a gas. It's like peering into the very soul of a material and understanding its essence. Quite the scientific marvel, isn't it? Stick around to learn more. So you might ask, what exactly is thermogravimetric analysis? Well, let's break it down. Thermogravimetric analysis, or TGA for short, is a method of thermal analysis in which we measure the mass of a sample over time as the temperature changes. This technique is part of a broader family of thermal analysis methods, which are all about studying the physical and chemical properties of materials as they change with temperature. But what sets TGA apart? It's all about the focus on mass. You see, as the temperature of a sample changes, we may notice a change in its mass. This might be due to a variety of reasons. Perhaps the material is losing moisture, or maybe it's undergoing a chemical reaction that results in the production or loss of a gas. By tracking these changes, TGA provides us with valuable insight into the thermal stability and composition of the sample. Now, why is this important? The applications are far-reaching, from analyzing the composition of polymers to studying the thermal stability of metals. TGA can even be used in the pharmaceutical industry to ensure the quality of drugs. In essence, thermogravimetric analysis is a powerful tool in the world of material science, offering a window into the complex interplay between temperature, mass, and the inherent properties of materials. Now that we know what TGA is, let's delve deeper into its types. There's more than one way to conduct thermogravimetric analysis. Indeed, just like the many forks that lead to fascinating discoveries in the path of scientific exploration, thermogravimetric analysis, or TGA, also presents us with different avenues. Two primary types of TGA are commonly employed: isothermal and dynamic. Let's begin with isothermal TGA. As the name suggests, iso meaning equal and thermal referring to heat, isothermal TGA is conducted under a constant temperature. The sample is held at a specific temperature, and the change in its mass is monitored over time. This method is particularly useful when studying slow reactions or when the exact timing of a reaction is crucial. On the other hand, we have dynamic TGA, which is a bit more, dynamic. In this type, the temperature isn't held constant but is steadily increased at a fixed rate. As the temperature rises, the sample's mass is recorded, allowing us to observe how it reacts to the changing heat conditions. Dynamic TGA is often used to investigate the thermal stability of materials or to identify the temperature range where significant mass changes occur. Both these types of TGA have their own advantages and are chosen based on the nature of the investigation. For instance, if you want to study the decomposition of a material, dynamic TGA would be your go-to. But if you're interested in understanding a reaction's kinetics at a particular temperature, isothermal TGA would be more appropriate. In essence, whether it's isothermal or dynamic, the type of TGA used can greatly influence the data obtained. The choice depends on the nature of the sample and the questions that the researcher seeks to answer. And with the right tools, these types can reveal significant data about our sample. So, in the grand scheme of thermogravimetric analysis, it's not just about heating and weighing, it's about choosing the right path, the right type, to uncover the secrets that the materials hold within. Truly understanding thermogravimetric analysis, or TGA for short, requires a closer look at the instruments involved. The TGA instrument is a marvel of scientific engineering, composed of several key components that work in harmony to perform the analysis. Let's start with the furnace. This isn't your ordinary furnace. It's a high-precision instrument capable of reaching temperatures upwards of 1000 degrees Celsius. It's here where our sample will be heated, prompting the chemical reactions that we're interested in observing. Next, we have the balance. This isn't a balance you'd find in your kitchen or your bathroom. This is a precision balance, capable of measuring changes in mass down to the microgram. As the sample is heated in the furnace, it undergoes chemical reactions that often result in a change in mass. The balance detects these changes, allowing us to track the mass of the sample over time. Then we have the sample pan. This is where the sample resides during the analysis. It's typically made of materials like platinum or alumina that can withstand the high temperatures of the furnace. The The sample pan is designed to hold the sample in place while it's being heated, ensuring that the balance can accurately measure the change in mass. Finally, we have the temperature controller. The temperature controller is tasked with controlling the rate at which the furnace heats the sample. By carefully controlling the heating rate, we can ensure that the chemical reactions occur in a controlled and predictable manner. These components, the furnace, the balance, the sample pan, and the temperature controller, each play a crucial role in the thermogravimetric analysis. They work together, each performing their own unique function, to provide us with the data we need to understand the thermal stability and compositional changes in our samples. The principle behind these instruments is just as intriguing as the instruments themselves. At the heart of TGA lies a fascinating principle. Let's unravel this principle, which is nothing short of a marvel in scientific exploration. Thermogravimetric analysis, or TGA, operates on a simple yet profound principle. It measures the mass of a substance as it changes with temperature. But how does it do that? Well, it's all about balance, a high-precision balance to be exact. This balance meticulously weighs the sample as it undergoes a controlled temperature program. As the temperature rises, the sample may lose or gain mass due to various physical and chemical phenomena. Now let's delve a bit deeper into these phenomena. When TGA heats a sample, it can trigger a series of physical changes. One such change is absorption, where a substance takes in another substance, resulting in a mass increase. Its opposite, desorption, occurs when a substance releases another substance, leading to a mass decrease. But the story doesn't end here. Decomposition, a chemical change where a substance breaks down into simpler substances, also plays a crucial role in changing the sample's mass. By monitoring these mass changes, TGA paints a detailed picture of the thermal stability and compositional changes of the sample. This data offers invaluable insights into the substance's properties and behavior under different temperature conditions. Armed with this principle, TGA finds application in a myriad of fields. From pharmaceuticals to polymers, from metals to minerals, TGA is a trusted tool in the hands of researchers worldwide. From pharmaceuticals to polymers, thermogravimetric analysis, or TGA, has a wide range of applications. Let's dive into the myriad ways this technique is employed across various fields. In the realm of material science, TGA is indispensable. It aids in determining the composition of materials, helping scientists understand their physical and chemical properties. For instance, it's used to analyze ceramics, metals, and composites, revealing the presence of any moisture, volatile substances, or organic content. Now let's talk pharmaceuticals. TGA plays a crucial role here too. It's used to study the thermal stability of drugs and other pharmaceutical substances. This analysis can reveal if a substance will decompose or react under certain temperatures, a critical factor in ensuring the safety and efficacy of medications. Polymers, though, may be where TGA truly shines. It's used to determine the thermal endurance of a polymer, meaning how long it can withstand certain temperatures before it starts to degrade. This is vital in the manufacturing process, ensuring that the final product can withstand the conditions it will be exposed to. In the field of environmental science, TGA assists in the study of soil and sediment samples. By determining the organic and inorganic composition of these samples, researchers can glean valuable insights into environmental changes and impacts. Even in the food industry, TGA has a role to play. It can analyze food products for moisture, fat, and protein content, contributing to quality control and nutritional analysis. To sum it up, TGA is not just a technique, it's a multidisciplinary tool, bridging gaps between various scientific fields. From helping engineers design more resilient materials to aiding pharmacists in creating safer drugs, to assisting environmental scientists in their research, TGA's applications are as diverse as they are essential. As we've seen, TGA is a powerful tool that continues to advance our understanding of materials. Next time you come across a complex material, remember there's a good chance TGA had a hand in its creation or analysis. So, stay curious and keep exploring the fascinating world of thermogravimetric analysis. So, what did we learn today? From the intriguing world of thermogravimetric analysis, we've journeyed through its definition, delved into its diverse types, and explored the instruments that make it possible. We've understood its guiding principle, and seen the vast spectrum of its applications. Indeed, TGA is a crucial tool in scientific research. Remember, science never stops exploring, and neither should you. Subscribe for more because you won't find me later.